Okay, so what we are discussed till now is the different biasing schemes of a transistor. Well, we have seen the different voltages at different points of the transistor. So this here is an NPN transistor with a voltage divided bias with R1 and R2, right? So what do you mean by R1 and R2? They're the biasing. They fix the biasing of the transistor. So what do you mean by biasing of the transistor? So we know there's a current. This current is flowing through the resistance and some voltage will be dropped across the R1 resistance. So this is V1, right? This voltage is V1, which is dropped across R1, and across R2 we have a voltage V2, right? So nothing but you can see the VB voltage is nothing but the VB. This is going to the input V2. So V2 is the VB, which is going input to the base part of the circuit, right? So now what is VB? We already know VB. This VB voltage here, this VB voltage I'm giving in the base, which is dropped by 2 resistance, is going to be given to the base. This is the input I'm giving to the base of this transistor, NPN transistor. Okay, 1 minute. Hello. Ah, yes, ma'am. Yes, ma'am. Yes, ma'am. It's audible? Okay, okay. Tell me. Yes. Ah, yeah. Is it audible?
Yes, sir.
ओके ओके मैं अभी मैं क्लास के बाद कॉल करता हूँ ओके ओके मैं कॉल में आ रहा हूँ ओके okay so okay so we have VB which is input to the transistor we put a transistor. So what happens is this VB is dropped across the base emitter junction of the transistor. So we know this is the base emitter junction of the transistor. This is base, this is emitter. So this VB we can write the Kirchhoff law. VB voltage is drop across VBE, voltage across base emitter plus V emitter VE, that is voltage across the emitter resistance. So again, we know in a silicon transistor, we know this is a constant around 0 0.6, 0 0.7, so I can call it 0.7 for simplification. Plus V is nothing but IE into RE, right? So again write this approximately equal to 0.7 plus IE is approximately equal to IC. So this is IC into RE, right? So I can see what I have done. I converted this approximated the IE is equal to IC. It's very important. So this is for simplification, although there is a slight error, but for all practical purposes, I can live with that error without any significant error or problems. Now we know the VB, we know the IC from here. So we already know the VB from the input voltage divider circuit, and we have this points when the IC, RC, RE also will be in the circuit. Now need to find the, so we have to find the IC from here. Okay, so once we get this IC, we can also calculate the VCE. So that VCE we already know. So what is VCE? VCE equation we have noted like VCC output equation. VCC equal to IC into RC, voltage drop across the RC resistance. ICRC plus VCE plus voltage drop across the emitter resistance, IE into RE. So this we know already. So again, this is equal to IC into RC plus VCE. We can find VC plus IC into RE, approximating IC equal to IE. Okay. So here, what are the knowns and what are the unknowns? Here the knowns are definitely we have IC we are getting from this equation. IC will get from this equation because we know VB, we can calculate VB because we have the 5 volt given, we have R1, we have R2, so we can calculate VB. So what is VB? I can write VB like this. VB is nothing but 5 volt, that is VCC, or 5 volt into R2 voltage divider, right? R1 plus R2, that we are getting from here. So I know got BT, I know this points, and Now I know the RE, so I get IC. So this IC I'll put in here, also here. So these 2 points I'm having IC. So all the things I know, RC I know the resistance, RE also I know. So I can find the VCE from here. Okay. So when I find the VCE, I got the operating point of a transistor. So what I got? I got the IC. I got the IC flowing through the output, and I also got the VCE, the output voltage of the transistor. So this is the fixing the operating point of a transistor. So from this, we are coming back to the load line, voltage load line. So now let's start the voltage load line. So based on these two things, I can draw the load line. So this is load. So this is voltage. So this is current. So this is current. We call IC. And now this is VCE, voltage collector emitter voltage. Okay, so now we can plot the different characteristics. Right now we have some particular point. So that point I'm marking here. Suppose I have a VCE equal to 3.5 volt and my IC is getting 8 milliampere. So this point I can mark here. This is the point, operating point of the transistor. Okay, so this point lies in some part of the base curve. So for example, this part of the curve maybe will be something like this. Say it is a part of some collector curve, something like this. Something like this. Okay, so this is corresponding to some IB, maybe IB say 8 milliampere by beta, right? That is IC by beta. That means basically 8 milliampere divided by some beta like 300 something like this. So this is particular IB. So this is my operating point. So from here I can see that my the output, even if I give an amplifier some signal. So right now what I fixed is my operating point. So this point, um, so this is called my operating point. It's my operating point. Operating point, or it is also called quiescent point, Q point. Q point. Okay, it's my Q point. Now what else? Now what I'll do? Now I should know that there are other points also within the same graph. There are different points with different IB, IBs. Some IBs going like this, with some IC going less than this. The different curves are possible. Okay, so I should know those things. So for right now, I'm a middle put. Now this is DC part. Now DC is fixed. Now I can go back to the my initial transistor. Now I'll see what will happen to the AC if I give the AC to the circuit. Basically, what is AC? What I'm trying to give? I'm trying to give a some small signal, fluctuating signal. May not be AC. It can be a small alternating signal, any sensor output or something. So this is my sensor. I present like this. This is fluctuating. So I'll just give this to a coupling capacitor. A coupling capacitor allow AC to pass to the DC circuit, but doesn't allow the DC to come to the DC doesn't come to the sensor circuit or the AC amplifier. Now this light wiggling, so sensor is sorry, slight sensor voltage. This voltage is going to change the IB slightly, or VB slightly, or IB basically. Okay, so what happens? This light changes here. We'll have a high changes in the VC part, or beta times change here, right? So what happens? So we get a better high voltage here. The small voltage here. The small voltage I'm giving here will be getting a higher voltage here. Okay, so and this, if I need to take it output, I need again another coupling capacitor or CC, and I can use some other block. I can block display or some kind of. So this is my next block. So this is the way I'm going to couple my AC to next block. Now what is the variation making here? The small variation IB will change the motion, change the IC from this to this. So actually, because the wiggling of IC is changing, right? So here IC, say for example, IB is less, IB is more than the 8 milli. Here 8 milli by 300. Here there is maybe this maybe say 12 milli by 300, somewhat greater. Right here it may be, for example, 4 milli by 300 something. So it is, IB is less in the bottom part, IB is greater in the top part. So this is the IB fluctuation. Based on the IB fluctuation, I have IC fluctuation. So IC fluctuation is like this much I have IC fluctuation. You can see this much is my IC fluctuation. Okay, so you can take the ratio. This IB is varying from 4 milli by 300 to 12 milli by 300. Sorry, this is not, yeah, this is milli by 300. It will be some micro, somewhat micro. But IC is varying from, you can see this is IC will vary from 4 milli to 12 milli. You can see the difference. So the difference in the IC is, delta IC is 8 milliampere, right? So a slight fluctuation in the base will cause a heavy fluctuation in the collector part. Now you can see the voltage. What about the voltage fluctuation? So as the IC is increasing, what happens? The IC is increasing, what is happening? You can see the equation here. As IC is increasing, you can see the IC is increasing. VC, what happens to VC? IC increasing means VC will be decreasing, right? This IC and this IC is increasing. That means voltage drop across these two resistances. That means RE and RC is increasing. So what happens? So this voltage VC will be decreasing, right? From this equation also you can see this voltage will be decreasing. Okay, so if this is decreasing, R is increasing, so we will come back to this. Or that means here, as IC is increasing, my VC is decreasing. That means VC is something like this. Here the VC is less. So here this is VC. So as IC is increased, VC is decreased, something like this, right? Because this is the new less VC, reduced VC. You can say VC 1 or something. Again, if the IC decreases, that means VC is going to increase. So this is new VC2 something. Okay, so we can see the IC is varying from, you can see IC, the left part, this is changing in this direction, and the voltage is varying in this direction, right? So this is the variation which I'm representing. So here from this, you can say, you can understand that my Q point ideally should be in the center of the load line. If you extend this line, this is nothing but the load line. So this point is VCC. This is 5 volt here. Again, extend this. Again, I get the maximum IC. That is VCC divided by RC plus RE. Right? That's the maximum possible current in that circuit. So this is my load line. So here we can see the Q point should be idle in the middle so that I have maximum swing. So this is a very important part of analog circuit that we need to maximize the swing, right? IC swing, and say for example we are discussing the Q point was here, we'll be cutting most of the VC wave because there is no possibility fluctuation here. So this point will be clipped. Same thing if you have a Q point at this point, what happened? Definitely the IC will be clipped, most of the IC will be clipped. So we don't want that. Okay, and it's definitely VC will also clipped here because VC is also very less here. Okay, I thought you got the understanding. We are trying to fix the DC first, then only we are giving this light AC from the sensor. So it get amplified because of the beta. Now we'll see the concept of a feedback. Like what is a feedback? So this is very important in op amp also. Next, I think next module will go to op amp. There also we use this concept of feedback. So here I'll just explain what is feedback. Suppose in this circuit, we initially had this circuit, base bias circuit, base resistance, and we have a collector resistance. This is plus 5 volt VC plus 5. This is RC. This is RB. Right now we are grounding this, and we have some base voltage also here. This is VB. Now, so right now the beta you can say is any value 200 or something. So we have some IV based on the VB. So here in this circuit, what happens if my beta is changing? Beta, because of temperature or something, beta is changing to 300 or 250 or something, whatever. So what happens? Initially, you can say this is IB. Some IB is there. This is, say, you can say this is 2 volt. VB is 2 volt, plus minus 2 volts. So this is, say, 1 mega ohm. So this is, say, 10 kilo ohm something. Okay. So here you can calculate the variation in current. Initially, we calculate what is beta, what is current at beta equal to 200. Say what current we are going to calculate? That IC and VC we are going to calculate. VC. Okay, so we'll get some value. How will calculate? We already know that we can calculate IB. IB is nothing but VB minus VBE, base emitter voltage divided by RB. So that we get from here, VB is nothing but 2 volt. 2 volt minus VBE, that is 0.7, that is for silicon. That divided by RB, that is 1 mega ohm. Right, this is approximately equal to, we can say, 1.3 microampere. Okay, so what about this now? IC, we know IC is nothing but beta times IB. So beta is 200 into 1.3 micro. This is nothing but 260 micro, or 0.26 milliampere, you can see. Okay, now this is the first current. So now the current is standard fixed at IC is 260, and we can also calculate VCE, right? Now, but because of the temperature fluctuation, say, let's calculate VCE also. VCE is nothing but, if you calculate VCE, this is my 5 volt minus ICRC minus, okay, that's it. VCI ICRC, 5 minus ICRC. That means 5 volt minus IC is 260 micro into RC is 10K. So this comes around 5 minus 260 is 0.2. 2.6 something. This comes around 2.4 volt something. Okay, this is my operating point. Okay, now let's see if the beta is changing. What happens? We can analyze what happens when the beta is changing. So when the beta is changing, the new things come. So we can see the new IB or new IB IC. New IC will be beta times 300 into previous IB. So it's increasing around, I think, 33%. So that is 300 into 1.3 micro. That is 390 micro ampere, right? So it's a considerable change in IC. So how much change in VC will come? VC equal to 5 minus ICRC. IC is 390 into 10K. So this will be around 5 minus 3.9. That is to 1.1 volt. This is nothing but 1.1 volt. So you can see how much change in the IC. IC has been changed from 2.4 volt to 1.4. So what happened? Now we should understand. Let's draw the this thing. Let's draw the load line Q point. How much change in the Q point has happened? So initially it was 260. IC was 260. For example, like IC is 260. This is 260 micro, and now the new current is 390 micro. So initially VC was how much? 2.4 volts. So it was 2.4 volt here, like somewhat in the middle, 2.4 or near 2.5, 2.44. But right now VC has reduced to 1.1 volt, more than half, 1.1 volt, right? So you can see this was our load line. So let me draw what is this case here. So initially you can say this was my load, sorry, this was my load line. Okay, so initial operating point was around middle. This is 260 and this is 2.4. Now it has been reduced to here. Now you can see this change happening. Now the operating point is here, which is not good. It is near cutoff, near operating point. So what happened? Because of beta variation. Why beta change? Because beta change because of temperature variation. right? Temperature variations, or we can say the current IC change and all those things. So this is not desirable. We design a circuit, we expect to operate in some region, but it is not operating in that region. So it's a big problem for us, right? So what is solution? The solution for this is, one solution for this is feedback. Now this is just introduction to feedback. We need feedback so that we have an inbuilt mechanism. As circuit parameters are changing, IP is changing, IC is changing. There is no mechanism to maintain or retrieve the old parameters. What should I do to make the transistor come back to the older position internally or without any external help? Right? So let's see. So this is undesirable. This is sometimes if the beta reduces, we can say this is will be new operating point. This is also undesirable operating point with less IC and very high VC. So here also you're operating in the cutoff region. So it's not good. Okay, so we'll discuss the concept of feedback. Okay, so let me change this base resistance to emitter here, right? So instead of this VB here, RB here, I'm changing RB to emitter. This will become RE. Now other things remain the same. This is RC. This is plus 5 volt. Okay. Now, let's imagine there's a beta change or the current is changing. Okay, so there is some voltage here, that is VBE. Okay, so I'll just explain the idea. What is the idea? So here the idea is VBE, VB equal to base emitted probe plus IE RE, right? IR. So this is nothing but we can simplify this approximately without any error, much error. VBE plus IC RE, right? I think this much is clear. Now, with this equation, now we have to explain. So initially the beta, for example, initially the beta in early case was 200, right? Now, if the beta is increased, if beta dash, beta increased to, for example, 300, a new value of beta is increased 300, right? So if beta increase, what happens? The IB will definitely reduce, right? IB will reduce. So sorry, beta is changing, beta is increasing, IB will be same, but IC is increasing. So right now I'm just drawing the load line left. Now this I'm using for this drawing. This I'm using the emitter character or input characteristics. Input characteristics. That is here. So this is VBE versus IB. Okay. Now what happens? We have different character. If you remember correctly, this is initially it will be very low, and at a particular point it is going to increase like this, right? Okay, so this is my VBE. Now let's see. This is with these two things. Let me analyze what happens with the beta changes to beta equal to 300. Right. So obviously, what happens? IC will change. So new IC is IC equal to. So initially we have IC something. So IC will also change. So IC is IC dash. The new IC is older IC into what? You can see it will be something like 300 divided by 200. This much increase because 300 is new beta and 200 is the initial beta. Now this increase in IB, what happens? This increase in IB, this new IC is increased. So this increase in IC, what happened? Okay, now come back to this equation. Come back to the earlier equation, right? This equation. This equation I'm considering. Okay. Now this increase in IC, what happened? Because of this because increase in IC is increased. What happened? This whole voltage is going to increase because RE is constant. Right? So what happens? VB is also constant, right? VB is also constant because this is fixed voltage. We are fixing the voltage. So what is the only thing change happen is in the VBE. Getting? This is the idea. This is the main idea I'm going to refer to here. Everything is fixed. IC is automatically increasing because of beta variation. and VB is fixed because this is coming from voltage source here. You can see this is full fixed. It's also fixed. So what is the only way you can follow the Kirchhoff law, voltage law, is by reducing the VBE. You're getting what I'm saying? So initially we had a VB like this, right? VB is like this. Initially it was operating this VB with some IB base current, right? Now because of increase in IC, you can see the equation, right? This part of equation is going to increase. This part of equation is going to increase, right? So what happens? The input is constant. This is constant. This is constant. There's no option to increase. So only option is to reduce VBE. So right now our VBE is going to reduce. There is no option but to reduce VBE. So what happens when VB is reduced? Now come back to the graph. Now VB is reduced. You can see that when VB is reduced, what happens? The new VB, I'll get new IB. You can see the IB is much less, much less. This is new IB, IB dash, IB dash. So what happens? Now IB is automatically reduced. This is actually what we wanted. This actually cancels the increased IC here. You can see increased IC is cancelled by the reduction in IB. So reduction in IB is cost reduction in VBE. This guy is reduced, right? Why? All this happened because I have a resistance RE here. There's a feedback. This resistor is giving a feedback voltage into the input circuit to reduce my IB. So this is the concept of feedback here. Now automatically you can see as beta is increasing because of temperature or any reason or IC, what happens? Automatically the increase in beta helps a or drops a heavier voltage, larger voltage, or IC is increased. So therefore larger voltage drop across this RE guy, RE. What happens? When larger voltage drop across RE, your VBE is going to reduce. Automatically it has to reduce because VB fix it, right? When VB is reduced, we can see the IB is automatically reduced. This is the diode curve. In diode curve, the junction voltage is reduced. So what happens? IB is automatically reduced exponentially, the exponential curve. So what happens? Now IB is automatically reduced. Now what happens? Now IB is reduced again as a reduction in IB, my what is reduced? My IC is also reduced. So as IB is reducing, this implies when my IC is obviously reducing, right? Even though beta is increasing, but my IB reduces, so IC is reduced. So when IC is reduced, what happens? IC is reduced, what happens? Automatically, VCs also get into the earlier version. So what happens is the increase in the collector current due to beta variation is nullified by this emitter resistance. It's called feedback resistance. So this is called emitter feedback bias. This is called emitter feedback, emitter feedback, feedback. I hope you got the logic of feedback, right? So this is the emitter feedback. So what we have done, we have drawn the circuit of base bias, replacing the base resistance into the emitter side. So what happens? Whenever there is a fluctuation in beta, what happens? More IC is flowing, right? Because IC is equal to beta times IB. So beta is changing, so IC is changing, but IC is changing. The voltage across the resistance RE is also changing. Based on this equation number one, I can say as ICR voltage across RE is changing, that means ICRC is increasing. That means VB has to reduce. VB has to reduce. So when VB has to reduce, you can know that from the base curve, VB reducing is IB has to reduce. So IB has to reduce so that my IC is automatically reduced, right? So how this happens? Beta increases by mistake, but V emitter increases. When V emitter increases, obviously V base emitter voltage has to reduce. This implies IB is reduced, so automatically IC is also reduced, right? So as beta increases, matlab what? IC is increased. So here IC is increased, and this effect of increase in IC is again nullified by the effect decrease in VBE. Okay, so this is kind of emitter feedback. Okay, now let's see what is the feedback. Again, if you have any question, you can ask, or you can ask last. So please. So now let's see the feedback in the voltage divider bus. This is RC. Okay, this is plus 5 volt. Again, we have R. Here also you can see the RE. Now we will take the supply from here only, and we have two resistance here. Okay. Now this is R2. This is R1. Now I can call this VB. No, here also let's we have a beta variation here. Initially beta was 200. Now beta is changed. Beta dash equal to 300 something. Now here also you can see what is happening. Here also, if I use another color, yeah, here also the VB is fixed. VB is fixed. Voltage divided by VB is fixed. We already know VB is plus 5 volt. Therefore, volt into R2 divided by R1 plus R2. This is fixed. Okay. Now, because of beta fluctuation, so we have initially Cara input Cara is like this. I'm just explaining the same logic by using voltage divider bias. This is IB. We know the curve is something like this, right? Now, because of beta variation, what happens? Because of beta variations, IC is going to vary. IC initially was IC. Now the new IC dash equal to earlier IC into new beta divided by old beta or something like this, right? So we can have that, but definitely it will be going to be increasing, right? So this is the new IC. So because of this new IC, what is happening? We have the voltage equation, the KVL equation, the output. So VCC equal to VC. This is ICRC. Sorry. So this. Okay. So we see, this is IC into RC plus VCE plus IC into RE. Approximately IC equal to I. Now, because of increase in I here, because of increase in I, what is going to happen? Because of the increase in beta here, we have already seen that the collector current is increasing. Because of the collector increase in collector current, can see increase in collector current, what happens? This collector current is increasing. So we already know the equation of base VB equal to VBE base emitter plus I can say ICRE, right? So this voltage IC is increasing means what happens? This guy is increasing. That means ICRC is increasing. So that means this guy is increasing. This guy is increasing and this guy is constant. VB is constant, but is constant. So what happens? There's no option to VB but to reduce. So when VB reduces, what happens? Initially VB was this much, giving a current of IB. Now it has to reduce, it will reduce to some point here. So what happened? Net, I have IB is also reduced here. IB dash is reduced. So when IB reduces, obviously what happens? IC is reduced. Then for showing that you need to draw the collector current. Collector current. Something like this. This was initial IC, but when IC increase, initial IC was this was initial IC, but when beta increases, it is increased to this point. But obviously, when the IB reduce, it will come back to nearby this point or less than that or something nearby that point, right? So we are getting a stabilized. Our current is not increased that much, and our load line is not affected much. Okay, so this is the concept of feedback. So I think this is the importance, and let's first of the more important concept of feedback we'll study in the op amp operation amplifier part. Now another important point I want to discuss with you is early effect. What is called early effect? This is a common interview question wherever you go. Someone can trick you on this question. So what is early effect? Suppose we are drawing the collector current. If you deeply analyze this, ideally what we have studied is the collector current is getting fixed at one point. This is what we studied. This is what studied. But practically, this is not the case. In practical, what happens is the collector current is a bit different than what it looks here. So this is IC and VC. But in real case, what happens is it is like this and starting and it is like this increasing slightly. Angle, some angulation. So here comes here and it increases like this is the real thing. Although we assume to be constant because saturation. So this active region takes the current source, translate the current source, assume constant. But here this is the reality is this thing. Now this effect is called early effect because of increase in IC, slight increase in IC as my VC is increasing. Now why this happens? Now this is the question. Now we have to go to structure of the BJT or NPN transistor to understand why this slight change in the current is happening. Okay, so let's see the structure of the transistor here. This is the emitter, so the base, very light, and the collector. Now we have the transistor of an active region. The base has to be this is NPN transistor, for example. This is NPN. So this has to be positive, forward biased. This is plus and this is minus. Same time, you can see that the collector, this has to be reverse biased. Any doubt? So this is reverse bias. Sorry, this has to be reverse biased. Now this is reverse biased. Abhijit Kumar, can you mute your microphone? Okay, so this is our active region where the base emitter junction is forward biased and base collector base junction is reverse biased. Now, because of this, because of this reverse bias, what happens is this is N region, this is a P region, right? So what happened because of reverse bias, we know this depletion region is going to increase. There's a base and base will be affected, and the depletion region is going to increase in the base, right? In a diode, PN junction diode, the PN junction diode is reverse bias. What happens? This is P, this is N. Now I'm going to reverse bias it. We have studied that when we reverse bias the PN junction diode, what happens? The depletion region is going to increase. Depletion region is going to increase, right? This is depletion region. Depletion region is going to increase. So same thing happens here. Because of the reverse biased increase in VC, I'm increasing VC. So remember, we are trying to increase the VC, right? We are trying to increase the VCE. VC is increasing as the curve is increasing. So VC increases means the reverse bias is increasing. So the more reverse bias is increasing with respect to the base collector base junction. So this reverse depletion region, the depletion region is going to increase. So what happens? Base, some part of base is going to convert it into depletion region more and more. So anyway, we know the base was already less, already thin. Now because of the depletion region, base becomes more thin. So those who are not understood, like those who don't remember, they don't remember that why base is thin, because base is made thin because we need less recombination in the base. The less recombination happens in the base, more electrons or current passes through the collector. So we have higher collector current. But here, already the base was less. Now the base is already reduced because of the depletion region, increase in depletion region. So why depletion region increase? Because of the increase in VCE. Increase in VC, what happened? Increase in VC, the reverse bias across the collector base junction increase. So because of the collector base reverse bias increase, your depletion region is increasing. So base width is decreasing. So base width decreasing means when the electrons from the emitter need to pass less base area. So again, the base recombination, the base current is going to reduce, or recombination going to reduce. So your IC is going to increase still, right? Less recombination. That is our idea. Less doping. We give less doping in the base and less thickness in the base, so that less recombination current or less current is passing through that part, so that we have more current in the IC, right? So what happens? Net effect, our IC curve, in the IC curve, we can see that as VC is increasing, our IC is not constant, it's slightly increasing, like this, slightly increasing. So this is called early effect. And to model the early effect, we add one more voltage, VA, early voltage, VA. Okay, so that will be discussed mathematically in the next class. So I think I'm planning to have a test, mock test. Mock test. I think, did you get your exam dates?
No, sir.
No, sir.
No, sir.
No problem, no problem. So, but we can plan some mock exams so that it will give you good practice for you. So maybe I think tomorrow also we can have a test, right?
So there is
Small
Viva tomorrow.
tomorrow.
Yes, sir.
Okay, fine. So maybe okay, now maybe after Viva we can keep this. Okay. Okay then, fine. I think this is sufficient for today. So you just refer the books. Malvino, you should refer. And Malvino, everything. Whatever we discussed, a lot of problems are in Malvino. You just go through it. And you can go to Bolstead also. Right? So that'll be good. Okay then. Thank you. You can put your roll number.
Thank you, sir.